In this video, we're going to do the second exercise of this worksheet, double integrals in polar coordinates. So let's scroll down to the second exercise here. This exercise is asking us, so question 2, to set up but do not evaluate a double integral in polar coordinates to find the area of each of the regions D below. And we're not given a picture, we're asked to sketch the region. So D is the region outside the circle, R is 3/2, and inside the circle, R is 3 cos theta. So we have to remember our circle equations from our curves here. R is 3/2 theta. No, just 3/2. R is 3/2 is centered at the origin. And here, so this is of the form R is 2a cos theta, which had its center along the x-axis, so at a and 0. So our a is 3/2 and 0, and the radius is also a. The radius is 3/2. Which means if we're going on the original circle, here is our center of the second circle. It has a radius of 3/2, so it's going to be like this, and going to come up centered on the x-axis and look something like that. So let's maybe add a little bit of color. Here is our curve. R is 3/2. So I'll add this guy in red, and the other circle in blue is the circle here. Okay, so now these regions, or these circles, compartmentalize or create different regions, and so we've got to be careful in what we're asked to do. We want the region outside the circle, R is 3/2, and inside the circle, R is 3 cos theta. So outside the red and inside the blue, that has to be here. So we're looking to find the area of that region. So there's a couple of things that we are going to put together to do that. And that first thing that we need to remember is that for any region D, the double integral over D of 1 dA, or just dA, is the area of D. So that's all we're going to do is we have to, if we call this our region D, we're going to find the double integral. We've got to find the bounds of D. Of dA, we don't need any function other than 1. Just the double integral of dA is going to give us the area that we're looking for. So what we need to do now is set this up in terms of polar coordinates. And so we have to imagine that we have here some angles, right? So here is our angle theta 1. Here is our angle theta 2. So that region is going to be going from theta 1 to theta 2. So how are we going to find what those theta values are? Well, they are going to be what happens at the points of intersection. And so points of intersection in polar curves, they act just like any other points of intersection. I want the intersection of the red and the blue. And so I'm going to take the red curve equation and the blue curve equation and set them equal to each other. So 3/2 is 3 cos theta. In other words, 1/2 is cos theta. And I can see from the graph here that I've got two particular solutions that I want. Theta is minus pi/3 and pi/3. Now it's important to be careful in how we choose these. If I want theta to go from theta 1, so that's what I'm calling this guy here, theta 1, to theta 2. I want to travel through my region in the order of theta. If I had taken theta 1 equal to 5, if I had taken theta 1 to be 5 pi over 3, and I had said that we were going from 5 pi over 3 to pi over 3, well, that's not the region that we want at all. 5 pi over 3 to pi over 3 would be going around this way. That's not at all the region that we want to capture. So we have to be very careful that we capture the thetas in the direction that we want to capture the region that we want. So we're going to take minus pi over 3 and pi over 3 for our theta values. So 0, no, minus pi over 3 is going to be less than or equal to, our theta value is going to be less than or equal to pi over 3. And then we have to look at the radius, right? From any radial point here, we need the radius to go from the inner curve to the outer curve, right? We want to capture all radiuses from the red to the blue, which means that our inner radius is the curve 3/2. That's going to be less than or equal to r, which is less than or equal to the curve in blue, which is 3 cos of theta. So if we put all of that information together, then the area of the region, the area, is going to be equal to the double integral, always thetas on the outside, so minus pi over 3 to pi over 3 of the integral from 3 over 2 to 3 cos theta of 1 dA, but dA in polar coordinates is r dr d theta. So we're not asked to evaluate that, so we're going to leave that as our final answer for question A. Question B. So question B is asking us to find the area of the region inside the circle r equals 1 and outside the cardioid 1 plus cos theta. So let's start out by drawing the cardioid first, because that is a little bit of a more complicated curve to draw. So that cardioid we had seen in class, but I had said I don't expect you to be able to draw that from scratch without sort of figuring it out what it looks like. And then so the curve, if we want to know here what this, when theta is pi over 2, then the cos of pi over 2 is 0. This is going to be at 1, and here will be at minus 1. So our circle is actually going to go through exactly those points. So my circle is not looking particularly circular, but you get the idea. And we want to be inside the circle r equals 1 and outside of the cardioid. So if we look at all of the regions bounded here, inside the circle and outside the cardioid is that region there. So there's our region D. So it looks like we should be able to go here from theta 1 to theta 2 here around this way to capture the region. It's looking like theta 1 should be pi over 2 and theta 2 should be 3 pi over 2, but we have to be careful again. Theta 2 is 3 pi over 2 is the correct direction. If we had taken, so not minus pi over 2. If we had done from pi over 2 to minus pi over 2, we would have gone around the circle in the other direction, and that is not what we want. So you have to be careful to label the coterminal angle in the direction that you want to go to capture the region. So let us again be more explicit though. Let's set this so 1, the two curves equal, find those points of intersection. So to set those two curves equal, 1 plus cos theta is my second. And so I'm getting 0 is cos theta, and indeed theta is any multiple, odd multiple of pi over 2. So those two values are indeed the right ones. Now we want the curves. Let's add a little bit of color here. So the inner curve is the cardioid. The outer curve is the circle. And so we want any radius to go from the inner curve to the outer curve. So if I were to draw a radius, I want it to go from the inner curve to the outer curve. And so the inequalities that we want for this region, well, we just said that it is pi over 2 is less than or equal to theta is less than or equal to 3 pi over 2 for the angle. And so for the radius, we're looking for the cardioid as the inner curve. 1 plus cos of theta is less than or equal to the radius is less than or equal to the outer curve, which is r is equal to 1. So the area of D is the double integral over D of dA. So giving theta first, pi over 2 to 3 pi over 2, integral from 1 plus cos theta to 1, not to r, to 1 of dA, and dA is r dr d theta for polar integrals, and this is the final answer as well. If we were going to evaluate, though, we would have to go as an iterated integral. There is no factoring because of these bounds, right? We'd have to go in order, the inner integral with respect to r, and then the outer. No factoring allowed for this one. Let's go on then to C. So C is one region inside, the region inside one leaf or petal of the rose. R is 3 sine theta. So what we need to do is graph this, and if you don't know how it looks, well, that's okay. Inside the region here, what you need to sort of latch onto is that the region, the petal, will start and end when r is equal to 0, right? R is equal to 0 is the beginning and the end point. When r starts at 0, and then the r is going to keep going all the way around, and then we'll end up at r equals 0 again. So we need two consecutive values of when r equals 0. So 2 consecutive r equals 0. Well, if r equals 0, 0 is sine of 3 theta. The sine is 0 when k pi is the argument, k pi, k for any integer. So k pi over 3 will be our theta. And so if we take the values of k is equal to 0 and k is equal to 1, we should see that our angle is going to go from here when theta is equal to 0 to here. This is not so perfect, but you get the idea. To theta is pi over 3. And then what happens with the radius to fill out this region? The radius needs to go, well, it's the full region, the full radian. So from 0 out to the curve. So the inequalities that are going to describe this region are, for theta, we're going to have 0 is less than or equal to theta is less than or equal to pi over 3. And for r, we're going to have 0 is less than or equal to r is less than or equal to sine of 3 theta. So again, the area of any region D is the double integral of the region over the region D of dA in either rectangular or polar. That is always true. And so if we're going to set this up in terms of polar coordinates, theta is on the outside, so 0 to pi over 3, the integral from 0 to sine of 3 theta of dA in terms of polar coordinates are dr d theta, and that is it. And just like the last example in B, if you wanted to evaluate this, you have to go in order and iterated integral, the integral with respect to r first, and then the integral with respect to theta.